It's actually my honor to have Professor Juhn-Jong Lin here to give tell us his recent work. So, I just learned that this the paper was actually published or sent to the PRB. Oh, Nature Communication. Sorry. Okay, last week. Let me briefly introduce the Professor Juhn-Jong Lin. Professor Lin obtained his bachelor degree in 1979, and then he went to, after the graduation, he went to Purdue University to obtain his PhD degrees, and then he spent time in the University of Michigan and Virginia University for postdocs. Then he returned to Taiwan in the 1988 as an associate professor in our department. Okay. 4 years later, he obtained his professorship also in our university. Then in 1997, he went back to a department of electrophysics. Then as a professor there. So today he is going to talk about his recent work. So let's welcome Professor Lin.
Yes, thank you. It's very nice to come to meet maybe not like old friends. Okay. So actually we have been working on this program for many years, but it's also very fortunate that it got the first piece of this work got published last week. And I have to confess that I volunteered to come here. I asked Xin Wei-Zhang to try to arrange a talk for me because I heard a rumor of a story that you had a speaker last semester or last year. The speaker claimed that there's no condensed matter physics, or condensed matter physics is dead. so I volunteered to come to give a talk on that topic in fundamental condensed matter physics. And the title is a bit long. This essentially is about strong electron correlation and many body electron systems. So, but the problem is also quite complicated. So I hope that I can give you some interesting story and some basic theoretical concepts. So this is already for a few decades. People are looking for interesting or more exotic signatures in quantum physics. And this work, experimental work, measurement was essentially done by my former PhD student and postdoc. Now he this year just got his position assistant professor in this College of Semiconductor Technology, NCTU. And the theoretical explanation of our experimental results, essentially we have very close collaboration with two German physicists, Stephen Kirchner and Hans Krohart. And okay, this is my lab. I like measurements and low temperature physics. And also I like a lot of wiring and piping. So physics knowledge through measurement. And today today the orbital Kondo effect was observed at around below 1 Kelvin or about 1 Kelvin. So it is about 270 degrees below zero. And this is low temperature power state. Also, we have access my lab to SEM systems. So we need SEM to make some micro electrodes onto nano devices to carry out measurements. So with this SEM, we can make, for example, small electrodes onto nanowires. Here is nanowires. The diameter may be a few tens nanometers, and length maybe a few microns. So we like to study a very small samples at very low temperature, and hopefully there are some interesting quantum phenomena. And today, I will keep talking about a few keywords: quantum physics or magnetic quantum physics, spin 1/2. And then we go on to non-magnetic quantum physics. And this is caused by some orbital coverage, but non-magnetic spin coverage. And we will also discuss about so-called one-channel Kondo effect. You have in the system, you have only one Fermi seed. And in some cases, you may be able to see two Fermi seeds or two conduction bands try to compete to cover with this local moment or in a quantum impurity with some two-fold designers, and that gives you a Kondo effect. So I will go through all this. And I will also keep talking about a dynamic defect, or sometimes called dynamic scaling centers. And for students, I hope you will become more and more clear what I did about these terms. For example, we are talking about real materials, real solid. So here is a solid, and we have atoms and bondings. And assume that if, for example, if one atom is missing, then this red atom, maybe you can, this atom can sit on the right hand side or left hand side. Actually, this atom can turn on or switch between these two sides. You can imagine that the energy will be similar, and they are close in space. So there's some probability for switching back and forth between these two equivalent sites. Or if you have some kind of disorder, and so this atom bonding between these two blue atoms, maybe you can sit also in the right, left side or right side. You cannot switch back and forth. And this can happen in real, or actually why they happen in real materials. So we have a defect. This is not some velocity. It is not fixed in space and time. It keeps moving back and forth. So we have a defect. And this defect has two equivalent sides in a solid. And that means we can model it by double wave potential. And depending on the material property, this double wave potential may be symmetric or asymmetric. So the basic idea about dynamic defect or scaling center is that you have an object moving back and forth. And in old days, many people believe that the object moving back and forth is an atom, or for example, oxygen vacancy. And nowadays, Okay, today we have a different story, and the moving object actually is an electron, because atoms are too heavy to give you a very fast fluctuating rate, or to give you a big enough energy scale. So we have dynamic scaling defects. This has two sides, and if conducting electrons coupled with this defect with an internal degree of freedom, then it can cause Kondo effect. Okay, this is non-Kondo physics. In real nano devices, some atoms maybe move very slowly, and this gives us noise. This is so-called 1/n noise. This is very slow moving defect or two-level systems. And if you have not just a single atom, if you have a group of atoms, for example, a nanoscale crystalline, the chance for it to move back and forth is very slow. But still, that can happen. So if that happens, and if you can catch the signal, it will give you this so-called random telegraph noise. And nowadays, when you go to smaller and smaller devices, this could be very, very important. So most people are working on a two-level system, usually are more interested in slow moving objects. But today we want to talk about something very fast, moving objects. So today I will talk about these two materials, iridium dioxide and ruthenium dioxide. And so here is oxygen here. So in real material, we can have oxygen vacancies. And in this system, we will observe some strong electron correlation effects. And that will give you some non-Fermi degree state. And we'll call it unconventional metallic state. And this unconventional metallic state we actually infer from the observation of Kondo effect, one channel and two channel and orbital. So this is long magnetic Kondo effect. This is basically what I want to discuss today. So the ground state is long Fermi degree ground state. But because most of the students here are maybe not familiar with condensed matter physics or quantum physics, so I will briefly introduce the theoretical development of Kondo effect. Kondo effect was originally discovered a long time ago, actually in 1930s, in Cameron Omnis group, the guy who discovered superconductivity. So in 1930s, they already found that in pure metals, gold, in this case gold, when you cool down to low temperatures, you see that the resistance increases at low temperatures. So this is very strange, because when you go to low and low temperatures, the lattice vibration should become less and less important. And so resistance should become smaller and smaller. If not, you go in superconducting, it should be constant. But here, there's a small resistance increase. And it took 30 years, almost 30 years, for this Japanese theorist, Kondo, to realize that this is actually due to coupling of the conduction electron, the Fermi sheet coupling with dilute magnetic moment. In this sample, you have a few isolated moments that are impurity. That impurity carries spin-off moment. So the conduction electron try to spin out to cover with this local moment, and that gives us Kondo effect. So you can find this in a solid state textbook, 30 years. And experimentally in the 1960s, actually people already found that the resistance increase. For example, in copper gold, you can talk with a small amount of magnetic impurity. You will observe Kondo resistivity increase. And then if you plot in this way, normalize the resistance increase and normalize the temperature to a so-called Kondo temperature, you can see there's a universal curve, some kind of universal behavior. And to me, it is quite a surprising goal. I'm not really working on theory. I don't know why or how difficult it is. It seems to get an analytical form of this function, this curve, or numerical form of this curve. For example, for numerical value, it took almost another 30 years. I don't know why it's so difficult. But anyway, this is developed along this time. So people already experimentally realized this behavior. But numerical renormalization group calculations can get this curve only in 1990s. And in this case, people are still focusing, or in their mind, they still only about one Fermi C and one magnetic impurity, or even not just spin-half impurity, the many-body interaction. So here I give you a very simple picture of our scattering of conduction electrons with impurity. Usually what we learn in solid state physics textbook is that we have defects because real materials always contain defects. So if we have a defect or impurity, usually we consider it as a non-magnetic and elastic scattering. Then, due to this scattering, we will have a resistance. And if you cool it down to a very, very low temperature, when there are no Coulomb vibrations, the resistance will come from this elastic scattering. And so we have a constant resistivity. We call it residual resistivity. But Kondo effect is concerned with not just an impurity. The impurity carries a moment. So this impurity can have a spin up or spin down orientation. So this is an impurity. We call it a quantum impurity with internal degree of freedom, other than 2-fold degeneracy. So conduction electron can scatter of this impurity, and they exchange spin orientations. And if you go through all the calculations, you will have this extra term ST exchange. Conduction electron spin, local moment, this impurity. And if we calculate this term, this ST exchange interaction, that will give you this resistivity increase at very low temperature. So that is the original idea of the Kondo effect. And when it goes to zero temperatures, the local moment will be further stripped by conduction electrons. So they form a spin singlet ground state, and this is returned to Fermi liquid ground state. So this is in 1960s by the theory by Kondo. 64, this work. But it is very interesting that in 1976, Kondo published another two papers together. He actually realized that you don't need a spin half. You don't need to have spin half. All you need is to have an impurity. That impurity can switch back and forth, a double wave potential or two equivalent sides. If this defect can switch between these two sides, then when it interacts with conduction electrons, you can also obtain this Kondo physics. You see, okay. In the original Kondo theory, conduction electrons spin, interact with this local moment. And then he realized 12 years after this original work, he actually realized that if you have a defect, no moment, no spin, but this defect can sit on the right position or left position, and this switch back and forth. And if their energy degenerates, then one electron coupled with this, interact with this. This actually also can be a fully mapped into the original Kondo Hamiltonian, and you will have exactly the same phenomenon. So this is this idea. So we just need an impurity having an internal degree of freedom. And this now is to coordinate state, non-spin, no moment. So the original Kondo physics, impurity spin flipping, becomes the problem of impurity side switching of fluctuations. We need two equivalent sides. In the simple case, it's symmetric double wave potential, but in real material, very often it may be asymmetric. And people model this as the two-level systems. So we realized that we don't need spin, we don't need local moment to cause Kondo effect. And then in 4 years later, in 1980s, the French group, very famous French group, they actually came to this idea that in the original Kondo spin-up Kondo problem, you don't need to constrain to one Fermi seed. They actually consider that if you have more channels, so-called channels of Fermi seed, and these channels will compete to a spin of this magnetic impurity. So there will be an overspinning of the moment. And if there's overspinning, can we still have a stable Fermi liquid state, or we cannot have no longer, we cannot have a Fermi liquid one state, and then there will be some kind of a so-called long Fermi liquid behavior. So they already got this idea in 1980. So the theoretical concept, the development is that original Kondo effect, you have one channel. And the ground state is Fermi liquid ground state. And according to this work, if you have more than one channel trying to compete to spin out the moment, then there will be some competition. And you will have some non-Fermi liquid behavior. And in recent years, many people, or at least some theorists, believe that this may be related to ITC superconductors in the normal state. Many people believe that ITC, the normal state property of ITC superconductor are non-conventional metals, so they call them strange metal physics. And they wonder that this strange metal behavior may come from or connected with this kind of multi-channel kind of physics. So 1980. And here is another mainstream, also one of the mainstreams of the Kondo series. 1983. 83. Zawodowski and his collaborators, they also realized that, or they formulate that according to this Kondo's orbital coupling, non-magnetic Kondo effect, and combined with this French group's multi-channel Kondo effect. Then Zawodowski and his collaborators, they actually worked pretty hard. In this issue, they published 3 papers in sequence. And the first paper, second, third paper, 80 pages in PRV. 14, 17 pages, really long work. And some years later, they wrote a review article, actually, 340 pages. So they worked so hard. And they proposed that now you have more than one channel, so you can have 2 or 3 more premises. And then you have a moving object, double wave potential, 2-level system. You move back and forth. And under this condition, you should realize 2-channel orbital Kondo effect. This is theoretical proposal. But in their mind, what they have is the moving object is a single atom, an atom. So I will not go into the details, but very simple picture is that if we have a magnetic spin-up impurity, then we have up and down. So the magnetic local moment can flip up and down. And if we have an echo, you can switch left and right. So you can imagine that this emitter could be equivalent. So either spin half internal degree of freedom over that side, right side, this can equivalent give you the Kondo effect. But here is the magnetic Kondo effect, here is the non-magnetic. And if you somehow you can separate or introduce more than one Fermi-seed, then you will have a 2-channel or 3-channel Kondo effect. And realize some non-fermitic behavior at low temperature. But Zawodowski's idea was heavily criticized by a series of a few theoretical groups, and they published a series of papers because there are a few energy scales get involved in the problem. And now theorists believe that a moving atom is the energy scale is not right, and the Kondo energy will be too small to be realistic, to be observed in the experiment. So this is rather than the theoretical concept, the development of a theoretical concept in Kondo physics. And what is interesting is that also around 1990s, we know that at that time semiconductor quantum dots become quite popular, and experimental technique become much better than the old days. So in around 1990s, people can make small quantum dots about 100 nanometer diameter. And if in this dot you have n number of electrons, then actually this actually behaves like a spin-up impurity. So source strength, this is Fermi-seed conducting electron. So you can have this coupling, and this is also a different version of Kondo physics. And they do observe Kondo conductance, but in this case, it is conductance. Because coupling of conduction electrons spin with this local moment actually enhanced transmission. So the conductance is increased, but the functional form is exactly the same. So in the original Kondo physics, because conduction electrons scatter off this local moment, so resistivity increase with decreasing temperature. But in quantum dots, in this case, conduction electrons are just coupled with this local spin and enhanced transmission, the conductance actually increase. So in 1990s, there's the new development of people call the revival of the quantum effect in semiconductor quantum dot experiments. The problem with this quantum dot is because the size is quite large compared with atom, so the counter temperature is very low, very low. And once people realize Kondo effect or one-channel Kondo effect in a semiconductor quantum dot, of course there are always some hardworking or smart guys. They immediately realize how to realize two-channel Kondo effect using a quantum dot. And here's one example, very famous example. So we have a blue, this blue Fermi sheet, and a quantum dot here without one, for example, one electron. So this is Kondo system. But you can imagine or design another large quantum dot here. So this dot is big enough that there are a large number of conduction electrons. So this is also essentially also a Fermi sheet, conduction electron Fermi sheet. And so this blue Fermi sheet want to couple with this local moment. This also want to couple this moment. So these are two Fermi sheets or two channels compete, and they try to observe two-channel Kondo effect. But in this case, it is still magnetic two-channel Kondo effect. So there are some signature, and maybe they observe it. When we have a Fermi liquid, the ground state, usually if we have some physical quantity change with some perturbation, bias voltage or temperature of magnetic field given energy, usually it is depend on the square of the perturbation, square of T or square of B or EV bias voltage. But in this case, there are theories. When you have some kind of non-Fermi liquid behavior, you will observe square root T behavior. So yes, square root T dependence. That's what they claim or they believe they have found two-channel Kondo effect. But in this case, you can see that there are many a lot of gating, back gating, top gating, and a lot source spread. So you need a lot of fine-tuning. It's very, very difficult. And so far, this may be the only report. Already more than 10 years, there's no second report yet. And this is quantum dots. So if we are interested in quantum materials or ITC, high temperature superconductor, we don't know how this kind of system are really connected with real material. We don't know the implication from this to ITC material. And again, as I said, TK is very low, so you don't have much room to go to approach ground state. Oh, okay. Yeah, if we have, according to the theory, if we have a non-Fermi liquid behavior or two-channel Kondo physics, we will observe, instead of T square dependence, we will have T dependence. square root dependent. But experimentally, it is very difficult because non-convening data, you need some balance in these physics parameters. In reality, when we work on real conductors, metals, or heavy lithography semiconductors, we know real materials are always disordered or weakly disordered, always contain a defect, even a small amount of defect. And in late 1980s, or in 1980, people also realized that Archer, Aronov, and partially man also made a very great contribution to this effect. They realized that in real materials, it is usually weakly disordered. That means we have defect. And if we have defect, then still states will be modified. And as a result of this slightly modifier suppressed then still state, a real metal always gives you at low temperatures a square root resistivity increase at low temperature. So when you observe this, most referees would immediately say that what you found is this two-channel counter effect. So it is very difficult how to distinguish or convince people that what you observe is a non-Fermi quick behavior or a normal conductors, but that contains defect. And okay, now I come to my system, our experimental result. We have worked on these two oxides for many years. It is interesting that they are oxides, but they are metal, very good metals. Not only from our measurements, energy band calculations also confirm that they are metals. So, for example, here's two ruthenium dioxide single crystals and two iridium dioxide single crystals. From room temperature down to low temperatures, you can see that as the temperature decreases, the dynamic vibrations become weaker and weaker. So we have a weaker and weaker skeleton, and then resistivity decreases. I got this from Vincent long time ago. He was really an expert in drawing single crystals.
He is well known in 2D area.
What's the difference between the the two curves?
Sorry. What do you mean
The ruthenium oxide, you have two, right?
Oh, this is the offset for clarity.
Just offset.
Offset.
Okay,
Offset.
they're the same.
Yeah,
Okay.
they're the same. What I want to say is that this, if you have very good crystals, no oxygen vectors, no defect, this is good metals. And if you go to very low temperature, here's below 10 Kelvin, you can see that it goes to a constant, resistivity goes to a constant, residual resistivity. So this is caused by this electron scattering with some elastic or static defect. And then if we take our oxygen out, we will see orbital Kondo effect, two channel and one channel. That's what I want to show. Oh, before going to my our experimental result, it is also very I don't know it is in coincidence, and I don't even know whether it is important or not. Because for so many decades, people try to observe orbital two-channel quantum physics in real material, but could not reach it. And I believe we have observed it. And what I want to say is that until last few years, people people have not talked much about topological properties. And in 2013, people found that these two materials actually have a large spin Hall resistivity. The reason for that theory is, this is what they say. I just quote what they say. They say that the large or unusual spin Hall resistivity are actually caused by the topological property. They have evidence showing that, or demonstrate that this material actually is Dirac not 9 meters. So my question is, so far I don't know whether this helps stabilize orbital two-channel Kondo effect or not. I don't know, but somehow it happened. Just last year they realized that this is Dirac not 9 material. So we studied iridium dioxide and ruthenium dioxide nanowire. We want to make a nanowire because then you have a larger resistivity and you can have a larger, higher resolution. So here's our nanowires and electrodes to send in currents measuring voltage and measurement system. So we have these nanowires and we do measurements, 4 probe measurements down to 50 millicade, and in magnetic field up to 9 tesla. Application of magnetic field is very important because if once you apply a magnetic field, if there's a big change, that this moment is there. If no change, it implies that there's no magnetic moment. So we apply this. And okay, this is just want to say that we measure these wires when there's no oxygen vacancy, and when we take some oxygen out, so there are oxygen vacancies. And by controlling the oxygen vacancy, we can have a residual resistivity, or we can observe Kondo resistivity. So this is experiment. The central panel. Here is a 2 ruthenium dioxide nanowires. So if there are no vacancies, perfect, or almost perfect crystal, then from room temperature down to low temperature, you can see this is very standard metallic behavior. Boltzmann transport equation, very standard. And then in either iridium dioxide or ruthenium dioxide, if you take some oxygen out, I will explain later after we have seen this experiment data. I will give you an explanation why oxygen vacancy give you this two-level system, and that will give us this orbital Kondo effect. So if we take oxygen out in iridium dioxide nanowire, if you look carefully or in large scale, you see that at low temperature resistivity increases. Here is a constant, and here it increases. And also in ruthenium dioxide, if you take some oxygen out, at low temperatures, you can also see a resistivity increase. So this is already some kind of indication that you have some Kondo effect. This is actually quite standard Kondo behavior, log P and then saturate. One the okay, sorry, later. So by controlling the oxygen vacancies, we can have counter-resistivity or no counter-resistivity. And what is most important today, maybe this figure. So in iridium dioxide nanowires, here, note that here is the square root T, square root of temperature. Because theories tell us that if you have this kind of non-Fermi liquid, two-channel kind of non-Fermi liquid behavior, it should have some kind of square root T dependence. So at higher temperature, above 20 or 30 Kelvin, here's the standard Boltzmann transport. But at low temperatures, resistivity increases, but not the scale. It is actually very small, very small. But we have a resistivity increases, square root T. And then in zero magnetic field, and in 6 Tesla, 9 Tesla. So you can measure in zero field and apply magnetic field. You can see that in this case, or in another wire. First, you observe square root T dependent. Second, when you apply magnetic field, there's no change. So there's no magnetic effect or no magnetic moment inside the sample. This must caused by other origins. And again, here's a different wire. If you put oxygen back, it will go back to this normal ratio resistivity.
How much difference in oxygen
Difference for what?
content? You said you take it out and put back in.
How many oxygen?
How much?
I have figured that maybe if I remember correctly, this is probably 0.03%.
0.03%.
This maybe takes 2 or 3 months. But I guess this is maybe in this topic, maybe one of the best set of data, and maybe the only set. So we observe indication of orbital two-channel Kondo effect, square root T dependence, and insensitive to applied magnetic field. Of course, we can rule out this three-dimensional electron-electron interaction effect, but I guess I will skip that. We can exclude that. So here's, sorry, this looks like a little bit complicated, but this is, so kinetic metaphysics for this. This is the crystal structure of ruthenium dioxide and iridium dioxide. They have effectively the same crystal structures. Here's oxygen, and this is metal, iridium. So, so this forms this triangle, isosceles triangle. For example, assume one oxygen atom is missing. So this is missing, and surrounding it is 3 iridium atoms. And this distance is slightly longer than this distance. So if one oxygen is missing, that means there are 2 electrons because they form iridium dioxide. So if one oxygen is missing, that means 2 electrons need to go back to this magnetic ion. So one missing electron give 1 electron to here, 1 to here. They don't want to take these 2 atoms because this is closer. Current energy interaction is stronger. So one must be go here and one go here. and here this and this are the same. And this one actually, this one atom in this crystal structure actually has the C4 symmetry. I guess I cannot go into the detail. If you look into the crystal structure, this is essentially a square. And it possesses C4 symmetry. And C4 symmetry implies that one dot electron goes back to this one, or this one, they are equivalent. If the electron goes here, he will sit at the phi d dxz or dyz orbiter. In this crystal structure, originally, if you have no oxygen vacancy, the iridium atom is the phi d shares up here. And now you have one electron. So this is, we call it defect electron. This is your quantum defect. And this defect have two positions, two orbitals to go. dyz or dxz. So that defect of scaling center gives us this orbital Kondo effect. Okay, it gives us orbital Kondo effect. But what is interesting is that in this iridium dioxide, because in this problem there are no spin involved. We are not talking anything about spin, no spin involved. So in this, in our conduction Fermi sheet, we have one half of the electron will spin up, the other half will spin down. These two, we can consider them as two independent and equivalent Fermi sheets, both of which try to cover or interact with this defect. So we have two channels spin up conduction electrons and spin down conduction electrons. They are equivalent but independent. And we have one defect. This defect, we have one scaling center. This scaling center is defect electrons. This electron can take either dxz or dyz transmission, and these two are degenerate. That's my best picture for why we have observed or why we explain our observation. Orbital two-channel Kondo effect. So again, very, very simple. Just to remind students, if you have a static defect in real metal or solid, you have a scaling and then ratio resistivity. If you have a defect, this is the magnetic defect, then you have a standard Kondo effect. So before and after scaling, this impurity spin flip directions. And in our case, we have no spin. Our scaling center can take either dxz or dyz orbital. And these two orbitals are degenerate. And so our spin down conduction electrons together with it, spin up conduction electrons also try to cover with, and they complete. It is very interesting, and we are very, very lucky that if we have only studied iridium dioxide, then this is fine and maybe good, but not as convincing. So we actually also have ruthenium dioxide. Ruthenium dioxide have the same crystal structure as iridium dioxide. And in this case, there's 40 electrons, and they also are degenerate. But somehow, this material is weakly anti-ferromagnetic. If it is weakly anti-ferromagnetic, that means that spin up conduction electrons and spin down conduction electrons are no longer equivalent and not degenerate. So we will have only one Fermi sheet. to interact with this effect. And then we should observe one channel orbital Kondo effect. And that is exactly what we have seen. So here is the ruthenium dioxide nanowires. In zero field, this is logarithmic temperatures. And if you go to very low temperatures, it goes back to T-square dependence. That's what I told you. If you have only one channel Kondo effect, when you go to very low temperature, you should go back to recover Fermi degree behavior. So should be a T-square dependence. So this is what we see. And in this case, for example, this curve, blue curve, light blue curve is the 1CK scaling from the numerical remote group calculations. So it actually collapses closely on this curve. And in this case, black symbols are zero field. Red symbols in magnetic field. You see again that there's no magnetic field dependence. There are some fluctuations, that's a different story. But we observe Kondo effect. Obey a closed state 1CK energy functional form. No magnetic field dependence. This also ruthenium dioxide nanowire. I guess this curve is even more beautiful. So in this case, we try to find a nanowire with a very low Kondo temperature. And so if you apply a magnetic field, 3 tests or 5 tests, this given energy is already larger than Kondo energy. So if this field is large enough, in principle, if your Kondo effect is due to spin off impurity, then you should completely separate the resistivity increase. And this is theoretical calculations that there's curve. There's that curve. These are calculations. But what we observe is it overlaps altogether. So in this case, because the depth is anti-ferromagnetic, weaker anti-ferromagnetic, time resolution symmetry is broken. So we go back to one channel Kondo effect. We actually have a few wires. And Kondo temperature varies from 3 to 8 Kelvin. But if you grow this reduced temperature, normalized Kondo resistivity increase, it was on the very vivid part, and 3 decades of temperature. It was very lucky because we got this curve a few years ago. We couldn't understand. In literature, old literature, it is always said that ruthenium dioxide is also non-magnetic. If it is non-magnetic, we should have observed a 2-channel. But somehow we always observe 1 channel. We really don't understand so many confused for a few years. But it was so lucky that just in June last year, people theory and experiment revised the over conclusion, saying that this is actually weaker antiferromagnetic. So we are pretty lucky. And again, now we can exclude the electron-electron interaction. So here is essentially oxygen content if if you want, we can calculate how many oxygen packets we have from this theoretical expression. You can calculate. Here's a few more minutes. I would like to talk this intrinsic storage. This is one example by from this college of Academy of Sciences. They collaborate with the Max Planck Institute in Dresden, and they published a few papers saying that claiming that they observed two-channel Kondo effect. And so there are one of the evidence they show that they observe square root T dependence. But of course, immediately after their publication, there are also people came out to say that no, you haven't observed two-channel Kondo effect. What you observe is square root T dependence is just electron-electron interaction effect. What I want to say is that either they argue for 2CK effect or oppose 2CK effect. Actually, both of them are cited my work. This is, and what I want to say is we measure this in Erhard in 1992. So we introduced a few aluminum atoms into titanium. So this is a defect scaling center. So this becomes a weaker disorder, and you should have a electron-electron interaction effect. So you see this is square root T dependent. So, So either this support or oppose 2CK effect. They actually cite this paper. And the experiment was done by my first PhD student, 1996, Gu Zilian. And we are still using this arc furnace to make samples. It is still working. And we still use the same this very cheap machine to cut samples. But this may be more interesting, this paper. So now, in the last few years, people are so crazy about quantum computing. And you know that probably you heard about John Martinez, the group came move from Santa Barbara to Google. So they work pretty hard on quantum computer. And in this paper, they demonstrate some quantum simulators. They cite in their references, they cite Feynman, Anderson, Densry, and Mark IV. This work. But actually, at that time we were so poor. We measure this curve from this equipment. At that time, Yang Xin and Professor Yang didn't support me so much. If they have realized, if Martin knew that we actually measure from this meters, probably would not sign it. Okay, just focus. But I'm quite proud of this square root dependent. Okay, there are also other reports, but people also came to criticism. So two-level system orbital two-channel Kondo effect. Zawodowski, our friend Zawodowski, I mentioned earlier. He really, I think he is a great physicist. He is a good friend of. He was a good friend of mine. He passed away 2 years ago. This is what he said to me a few years ago, long years ago. But the true story for those who can read Chinese. He used to tell me these stories. So in order, we have worked on this for a number of years. But it takes also many years to understand, to find an explanation. And essentially, theoretic work was done by Stephen Kirchner. And they Max Planck Institute at Dresden, they set up a joint center on strong correlation, strongly correlated material in Zhejiang University. So they visit Zhejiang quite often. So in the last few years, besides this year, I also either went there to discuss with them or invite them to come.
Is that bottle beer or still water?
Beer.
How many bottles?
16.
16.
That is, here is 12 because
So
people already get away for starters, so the beer,
so that gives you an idea.
It's a Qingdao or
那是500或600 cc， 不是350。
是青岛啤酒，
我忘记了。
还是硬件？
But you see, it's a long. So he did experiment. They did theoretical interpretation according. There's some media report yesterday. Our paper got published on last Monday. And it is very strange, very crazy. Now the university are really crazy. They want to go for a ranking, worldwide ranking. So this was published on Monday. And on Tuesday, NCTU University Press Office or something like that asked me to write something. So I wrote a short article for them on Wednesday, probably. And they modified it and finished it on Friday. And so this Monday, they released it too. But what I want to say is it is interesting that the title I wrote is this. I think it is correct because people has been searching for orbital contact effect for at least in the 1970s. And we are very clear now. And this is the title from the modified from NTU press office. And then yesterday, I think China time is okay. The title is also okay. But in Apple, they become on this is okay, I guess my story today is that we work on iridium dioxide and rubidium dioxide nanowires. Because these two systems contain 240 zeros came from this defect electrons. And this so-called quantum impurity with an internal degree of freedom give us Kondo physics. And this is non-magnetic. And really, it was so fortunate for us that we have these brothers, really twin brothers. One is non-magnetic, one is weakly antiferromagnetic. So here, time reversal symmetry is reversed, so we have two chambers. Here, time reversal symmetry is broken, so we return to one chamber. And yeah, Kondo formulated this idea. The first idea in 1960. 77. Okay, thank you.
Now the floor is open for questions. Yeah, I'm interested in the fluctuations. One of the plots. Yeah. There's another more, right? Besides those. Yeah, like this one.
This is actually universal conductance fluctuation. I don't know.
But why only show up in the when you have a 4 Tesla? The black when 0 Tesla almost nothing.
In zero field there are also fluctuations, but in this case you average it.
Oh,
We average out
okay.
just to demonstrate to make it not so complicated.
Okay, I see.
Universal conductance fluctuation.
So any more?
So in this scanning time spectroscopy, people have used that technique to, for example, see this Kondo peak at the Fermi energy. So when you have these two channels, Kondo effect, you would expect this SDS signature would be very different.
In principle, physical should be the same, right? Or what related, but I don't believe. I guess it is very difficult to do SDS experiment on these kind of things because the signal is so small. I guess the SDM is very difficult to resolve the signal.
Yeah, but SDS is very local. It's looking directly right at the Kondo.
Yeah. But from experimental point of view, resolution is not high enough, and they cannot go to very low temperatures. And I don't know whether maybe they also have a difficulty if you apply a deep field, maybe also affects something. So this sample actually are quite clean. They are almost single crystal. So you want them to be clean, and then there's no or very weak electron interaction. But on the other hand, because they're so clean, so you want to make the sample very small, narrow wire, so you can have a high resolution for to measure resistivity.
I'm curious to say that orbital Kondo effect does not depend on magnetic field.
Right.
In the example, or say the upstream vacancy, you have an unpaired electron, right? So if defect have an unpaired electron, so if you apply magnetic field, the unpaired electron will align the polarization will align along the magnetic field. Therefore, you have the magnetic property. And so electron scattering with the polarized impurity, then the scattering coefficient or scattering cross-section will be different. So intuitively, I would expect the resistivity would depend on a magnetic field. Even though this picture shows it does not depend on magnetic field. However, in some of your data, it shows a weak magnetic field dependent, even though you say it does not depend on magnetic field. Yeah, here. So for example, this one. The black one is the V equal to 0. However, in the 3 and 5 Tesla, you see it shows a weak dependence on magnetic field, right?
I don't know the theoretical details, but of course, physically, there must be magnetic field effect. But the intuitive effect, but that effect maybe, I don't know, 1 or 2 more, a few order magnitudes smaller.
Yeah.
That would be higher order effect, much smaller than this.
Also, I'm just curious. Say intuitively, I would expect the resistivity would depend on magnetic field, because the defect always have an unpaired electron.
Yeah, right, but that must be a higher order effect.
Okay.
And theory have only conclude that you need a much higher field than this kind of energy.
Okay. Okay, so my intuition is correct.
Correct, but very small.
Okay.
All right. So if there's no other questions, let's thank Professor Lin again.